Okay, so in this one we're told that the length of the well is 0.50 nanometers. And we're asked to, first of all, calculate the wavelength of the photon which is released as it goes from the third excited state to the ground state. And we've just shown that 1 over lambda is equal to h over 8mcl squared times the initial quantum number squared minus the final quantum number squared. Okay, so let's work out what this term out the front is. So h, that's 6.626 times 10 to the minus 34 over 8. Now m, it's a trapped electron, so this mass is the mass of an electron, 9.109 times 10 to the minus 31, times c, that's the speed of light, 3 times 10 to the 8, times L squared, which is 0.50 times 10 to the minus 9 squared, and then we'll have Ni squared minus Nf squared. So solving this on the calculator, we end up with 1,212,354. Let's just keep all our significant figures for now, times the quantum number of the initial state squared minus the quantum number of the final state squared. Okay, so now all we need to do is substitute in our different cases. So in case A, we're going from the third excited state. Now the little trick here to remember is that the third excited state actually has n equals 4. So the initial quantum number in this case is n equals 4. And the ground state, that's n equals 1. So we're going from n equals 4 to n equals 1. So we've got 1 over lambda is equal to 1,212,354 times 4 squared minus 1 squared. Solving this, we end up with 18,185,311, and this is 1 on lambda. So inverting that, we get lambda equals 5.50 times 10 to the minus 8. And so this is around about nanometers, so let's present it in nanometers. So this is equal to 55 times 10 to the minus 9, so 55 nanometers. And we've now given that to two significant figures, as L was given to two significant figures. Okay, now part B. In part B, we're told that we're going from the second excited state to the first excited state. So in this case, our initial I, second excited state, so that has n equals 3. First excited state, the final n is going to be 2. And so we have 1 over lambda equals 1,212,354, this same number again, and then times n initial squared, so that's 3 squared minus n final squared, which is 2 squared. This is equal to 6,061,770, which tells us that lambda is equal to 165 nanometers. That's to three significant figures. It was actually just below this, so this is equal to 160 nanometers to two significant figures. Okay, and then finally C. In this case, it's jumping up levels. So in this case, it's going to absorb the photon, and we're going from the ground state to the second excited state. So because it's being absorbed, we actually end up with the opposite sign. So we effectively switch these ends here. So we have 1 over lambda is equal to h over 8mcl squared, which has the same numerical value. It's equal to this. And then we'll have nf squared minus ni squared for a photon which is absorbed. Okay, and in this case, we've got the initial state is the ground state. So initially, n is 1. The final state is the second excited state, and so that has n equals 3. So we have 1 over lambda is equal to 1,212,354 times nf squared. So that's 3 squared minus ni squared, 1 squared. And so this is equal to 9,698,832, which tells us that lambda, just inverting it now, is equal to 1.03 times 10 to the minus 7. So in nanometers, we can write this as 103, which to two significant figures is 100 nanometers. Okay, so that's how we solve that problem.